Since some students has asked about how to compute the private key or how to get the D, in particular this question, I'm using this video to show you an example similar to our exam question. Let's say the setup is P equals the two primary numbers, 17 and 31. Then you have N equals this, and then you need to compute the totient, which is actually their online facilities compute this, and which I get 480, which means the relative prime numbers to this. That's this many. Then let's just review the setup. How do you do the SAT? This is how you actually do. Okay, and then how do you prepare this? You prepare the sender and prepare a public key and E and N private key, both private by the request message. And then you give the public key, because nobody captured this, it doesn't really matter, captured it. So you give it to your partner, and he does this. Get a code, he has a message, and then code it, and then send the message E to the mod, and goes back, and then you do this mod on this side. You get back the message. So, summarize, you will have prepare a public key and a private key and this N. Then they send the public key, as you don't have to worry somebody will capture this because he encapsulated the message, but then they don't know how to break the message. But then you also have a private key to prepare, and then you use the private key to do this operation on this, and then you get this back. So I'm sure you know how to do this. Let me write it clearly. So how you get it back, you get the message, and then you get the code on the sender side, and then get mod, and sorry for my writing. So now you need to compute the D. So you know E, you choose one that has to be relative to prime to this, and you can use some online facility to find out the list of numbers that relatively prime to 480, which is again the totient of this. And then you pick 17. You can see that 17 is among the list of those numbers. You can pick any. So then you have important things what to choose for this D, which means you divide this, the remainder, divide D times E, and the remainder is N. So if the number is small, it's like 25 and 17, and then you can sort of guess. Now, if the number is big, and some students will ask, how can I get it? So actually, as we learned how to calculate the large exponents, modulus of large exponents, you break into small pieces. But there is actually an algorithm, and there's a trick to do this. I'm going to go over this particular example. So the key has to actually satisfy this requirement. So E times D mod 480, not of N, sorry, that's 480. That's actually totient of N. So that's 480 equals 1, the remainder 1. But you definitely cannot keep on doing the division and always try. So how do you do that? And then you will see, imagine this is basically algorithm in number theory. Here is how you find it. You see D equals 1 plus some number times 480. So divided by E. All right, so if you get a whole number, but with a division, K is some integer. K is some integer like 1, 2, and so on. So see if that's integer, if you then the E is integer, you divide it. Obviously, if this you get an integer, then you solve the problem. So then you just have to try different number of K. Okay, let's see K equal 1. So then D, okay, 1 plus 480 and divide by E, and then you get 28.29, for example. Oh, no, D cannot be this, because the the remainder cannot be 1, so D cannot, you get this. Now you try k equal 2. Then 2 times, then divide by 17, and then you end up with 52.5. It's not a whole number, so it doesn't work either. Then you try k equal 3, you get 84.7, and then finally you get k equal 4. Then you do the same thing, that number is 4, and you end up with D equal 113, which is a whole number. And then you get, if that is satisfied, see, if this get a whole number, then you can prove that this condition is satisfied, which means E times D mod 480 equal 1. So then that's a procedure to find D. So you can imagine that why this RSA is hard to break. If we use small number, you can even do it by hand. Imagine this process. If this number is huge, it's like 200, 100, 1,000 bits, and then this process will take forever. And also it takes a long time. Even if I give you the N and E to calculate this totient will take a long time. Very, very long time. It takes maybe a month to get it with the computers. But of course, you get the idea with the small numbers. So once again, you just do D equal 1 sum K times the total 480 divided by E, which is now chosen to be 17. You just try K equal 1, see if you get a whole number. 2, if you get a whole number. And then we are all computer science majors. You can easily write a computer program. In fact, if you search online, I shouldn't be giving you this, but you search online, you call it modular inverse. So then there's already a program. I wish every one of you would be one of those guys writing those programs. So you are learning this algorithm here. This algorithm is very simple. You keep on trying different K until you get a whole number. So of course, the number I give you for the exam are small numbers. You can finish real quick. So then you search this modular inverse. Here we have D is the modular inverse, mod inverse of E. So basically you insert online, you give E and N, and then here is 480, and then you get D. So I'm not encouraging you to do that. You do it by hand. I want you to be a programmer who can write such a code. But here you can even calculate it by hand. Hope this is helpful. I tried a little bit sloppy, but since this is exam, I don't want to give you too much. I think this is good enough. All right, have fun.